Hey, what's up, guys? This is Chung here. So today's daily challenge problem, number 105. Construct binary tree from preorder and inorder traversal. Very classic tree problem, right? I think everyone knows what is the preorder and the inorder traversal, right? So preorder traversal is like we visit root node first, and then left, and then right, right? And for the inorder, we visit the left first and then right, then root and then right. Okay, and given preorder and inorder traversal, we need to reconstruct the original tree, right? So for this problem, so to me, I think the preorder is the most important one because if we follow the preorder sequence here, that's exactly the sequence we're going to use to build our tree, right? For example, this one, the first one is 3, which means 3 is the root node, okay? And then the left one, the next one is 9. The 9 is the one that we want to attach to 3, which is in the left child, okay? And then 20 is the next one because 20 is the right child. We're going to append because there's nothing under 9. That's why the next one is 20, right? And then 15. Okay, 15 is exactly the next tree node we're going to create, which is this one, which is the parent, which is the child node of 20, and then 7 in the end, right? That's why this preorder to me is more important, but only giving this preorder will not be enough for us to reconstruct the tree, right? Because the tree could also be like this, could be 3, 9, 20, 15, and then 7, right? So this can also be a tree. And the preorder for this tree is also this sequence. Okay, so that's when this inorder list comes to rescue, right? Basically, we need this inorder traversal to help us determine if, given the current node, we want to know if this current node has any child. That's when we need to use the second one. And the reason being is because, let's say, for example, we have 3 here, right? So 3 is this. So we have a 9, 3, 15, 20, and 7, right? So 3 is the first one that we're going to process, and 3, this is the index for 3, right? So we know by looking at the 3, every time basically we split this inorder traversal list into 2 parts, where the left part is it's everything on the left side of the current root, and this part is the right side on the current root, right? That's why the next one is 9, because we know they're like a child on the left side of 3, right? And then when it comes to 9, we want to know, okay, so 9 doesn't have a child. So how can we know that? Because because when we process 9, we're in the range of this part, right? And this part we have a range where it's from 0 to 1, I think, assuming this is a range, right? And then we want to see that between 9 and the left, do we have any other like numbers? If we do, right? If there's anything between the range between the left border and the 9, if there's like any numbers here, then we know, okay, 9 has some other has a left child, right? And if there's anything on the right side of 9 between 9 and 3, then we know this part will be the right child of 9, right? That's why every time when we're processing a number here, we'll be using we'll try to find the index in order, and then we'll use the left and right boundary, right, to check if the current node has any left or right child. And that's basically the idea here, So, and in order to check, since for each of the node we have a boundaries for that, right, between the left and right. That's why when we write the DFS here, we need 2 more index here, right, or parameters here that can tell us the boundaries of the current node. And then since we're going to process the preorder in a sequence, we can simply do this. So every time when we are at a DFS, we can simply do a preorder, dot pop 0. Yeah, I'm assuming this one is like off one, but in reality it's not. But I'm just using this one just for this simplicity purpose. And then every time we have a node, we simply it's going to be a root, right? It's going to be a tree node of value, right? And then we need to find the index of the current value in the Inorder traversal, right? Give me Inorder dot index of value, right? And then we're gonna have like a node left equals to DFS left dot I minus 1, right? And then node dot right equals to DFS of I plus 1 dot right. And then in the end, I return the root. So here, like I said, given like a current values, we need to know if the current one, if this value has any left tree or right tree, right? So we do so by passing in this kind of the boundaries for the left half or the right half, right? Because here we already have I here, that's why the boundaries will be I minus 1, right? And I plus 1 here. And obviously, if there's no left or right subtree, we need to set a none here, right? Otherwise, we recursively calling this DFS to process the to process the subtree, right? So the base case will be if the L is greater than R, right? We return none, right? For example, if we have 9 here, right? If the current value doesn't have any uh, children, basically this L, if this one doesn't have any children, it means that L is equal to R, because it's the node, it's by itself, right? So which means every time we do either do a I minus L to I minus 1 or I minus 1 to R will both lead to this none here, right? So yeah, and that's it. So we have this. We can simply return here. So it's going to be n dot length of preorder minus 1. Okay. Yeah, that's it. If I run the code, right, submit. Yeah, there you go. Right. I mean, it's very classic, a DFS tree problem, but this time it's in the reverse way, right? Basically, you're given like a pre-order and in-order traversal list, and then you need to reconstruct the original tree. So basically, we use a pre-order traversal as a main source, because this will be the sequence we constructing the tree node. And then in order to reconstruct the tree, we need to know if the current one has any child or not, right? How can we check? We simply use the range for the current subtree plus just use the current range of the subtree, and then to check if the current one has any child. Because in order, if we find the index for the current values, we can know how many nodes we have on the current node's left or on the current node's right, and we can use that to to determine if the current one has a left subtree or not. And that's it. Cool. It's not that difficult, but I believe this is quite interesting and better to understand the concept behind it. Cool. Thank you for watching this video, guys, and stay tuned. See you guys soon. Bye bye.